All right, so we have now come to the end of radiation, and so do a radiation review today. So chapters 12 and 13 were the ones that covered radiation. So obviously, exam next class, deal with that first. So chapters 12 and 13, like I just said. So the basic stuff, view factors, the radiation wavelength relationships, and the radiation networks. There's no numerical solutions, so the last lecture content will not be on it. There's also no reflecting media, so the lecture right before that, a week ago, the second half of that involving those really complicated radiation networks involving reflection will not be on it as well. As usual, it is open book. Again, you're going to need a few graphs. There's those tables involving the wavelength relationships. There's the graphs and equations for the view factors that might come in handy for those. As usual, 75 minutes. There'll be less questions this time though. So last class, or last test, I mean, there were a lot of people thought maybe there's too many questions, a little bit too long. So it's going to be shorter this time. Instead of 10 multiple choice questions, there's only going to be 5 multiple choice questions. And then there's going to be 2 open questions, what I call a medium open question and a long open question. So these will be actually longer than the open questions you had before. Kind of examples as to what all these are going to look like. At the end of this will be a few examples from a previous test. So the multiple choice ones will be like example 1, nice, easy, simple, kind of one calculation, one equation sort of question. The medium open question will be kind of 2 or 3 calculations. And then the long open question will, as you'll see, involve multiple calculations. So review of radiation, standard black body radiation. I have my total energy emitted, EB, per unit area, sigma times T to the 4th. So again, that's for a black body. It's assuming all the energy is allowed to leave the surface. Sigma is the Stefan-Boltzmann constant, 5.67 times 10 to the -8 watts per meter squared, Kelvin to the 4th power. And now normally, if I don't have a black body, not everything's being absorbed. I have a combination of reflection, transmission, and absorption. And so all those 3 things, reflection, absorption, transmission, have to add up to 1. So the total energy fraction has to go into one of those 3 places. And my absorption is always the same as my emission. So epsilon equals alpha for every material. Then these wavelength relationships for gray bodies. So the fraction of total energy radiated between 2 wavelengths. So for this case, it's 0 and some wavelength lambda. You can get these fractions, EB from 0 to lambda, or EB from 0 to infinity. So this total fraction are the ones that are given in the table in chapter 12. And that's basically integrated energy from 0 to lambda divided by the total energy from 0 to infinity. So again, it's not table 8-1, it should be table 12-1, I think. All right, I stand corrected. That is table 12-2 on pages 554 to 555. In the table, the column we care about, this fraction basically is called F0 to lambda. And so if I want it between 2 wavelengths, so this is from 0 to lambda, what I can do is I can take it from 0 to the second wavelength and subtract away 0 to the first wavelength, and that's going to give me that increment between lambda 1 and lambda 2. And then this EB from 0 to infinity, EB from 0 to infinity is my entire total energy being emitted for a black body. In other words, sigma times T to the 4th. So sigma times T to the 4th times these 2 F0 to lambda is essentially for the second wavelength minus the first wavelength will give me that total energy emitted between the 2 wavelengths. And the second topic we dealt with was the radiation view factor. So basically, I have these bodies, they're emitting this energy in all sorts of directions. And if I want to look at the interaction between 2 of these objects, whatever energy gets emitted from the first one, I want to make sure that actually hits the second object, because any energy that doesn't hit the second object is not going to be part of this interaction. And so the radiation view factors tell me essentially how much energy leaves one surface and hits the next surface. So Fij, the fraction of energy leaving surface I, that actually reaches surface J. And then due to symmetry, area 1 times F12 equals area 2 times F21. So essentially, am I looking at how much energy is leaving surface 1, hitting surface 2, or the other way, F21, how much energy leaves surface 2 and actually hits surface 1. These guys found in tables or graphs or equations, various shapes and orientations, pages 603 to 607 in the textbook. There's various figures and, as I said, graphs, equations there. One thing to be careful of is which one's actually called figure 1 and which is actually called figure 2 in the table. So want to make sure you're actually doing F12. If you're asking for F12, make sure you're not actually calculating F21. So make sure that orientation is the same. Otherwise, you might end up with the wrong answer. So those give some simple geometries. Sometimes you have some harder geometries. So things like this two adjacent walls, 90-degree angle between them. So this orientation is given in the table. So I can find F13 from the table. But what if I want something that looks like this? So I have a gap between these two objects. So this orientation is not given in the table. But what I can do for situations such as this is do a algebraic expression. So if I want to find this guy here, I realize that this guy here added to this guy here gives me this combination. And this combination is essentially the same as this combination in terms of the geometry anyway. And so for the tables, both of these guys are given. Essentially what I do is just count 1 and 2 as one object. So 1 and 2 as one object. That's what I'm calling F3, 1, 2 in parentheses. So those guys are counted as one object. And I can then find the view factor, F3, 1, 2 from the tables. I can find this guy, also F3, 1 from the tables. And then essentially that's going to give me the one I care about, which is F3, 2, by taking the original one, F3, 1, 2, and then subtract away. So move this 3, 1 to the other side, and that's going to give me the one I want. So more complicated geometries can be found through this, what I call geometrical analysis. So standard radiation problems, you end up with radiation networks. So you either have 2, 3, 4, 5 objects, however many there are, all could possibly be interacting with each other. The most common one we saw were 3-object radiation networks. We also saw a lot of 2-object radiation networks. Those are a lot easier though. It's just a linear system from one to the second one. So the 3-object radiation networks, a bit more complicated, mainly because object 1 interacts with both object 2 and object 3, and same thing for object 2, interacts with both object 1 and object 3. And so I had to have this triangular sort of network, and it ends up with these J's. So basically J, remember, is my total energy being emitted from the surface. And so at this EB, my black body, not necessarily all of that is being emitted because I have an emissivity that may not be equal to 1. And so my emissivity is not equal to 1. There's going to be some resistance. And so each of these orange lines has a thermal resistance associated with the energy actually being able to leave the surface through this absorptivity or emissivity factor. And so 1 minus epsilon over epsilon A is that resistance to essentially leave the surface or to get to the surface. Then once I'm at that surface, I can interact with all these other objects, and those interactions will be basically down to the shape factors. So how much of this radiation that's leaving my surface, all my J's, is actually hitting the other surface. So from J1 to J2, for example, I have 1 over A1 F12, or conversely 1 over A2 F21, because those are the same thing. So each of these green lines interacts with a resistance that looks like this, 1 over A times F. Each of these orange lines basically has a thermal resistance, 1 minus epsilon over epsilon A. And you can do that, you can generalize this to more than 3 objects, or even down to 2 objects. So leaving the surface, I need to get to my J, have this resistance, need to get to the next object using the shape factor, and then it needs to be absorbed into the object, again using that same 1 minus epsilon over epsilon A resistance. Then once I figure out, or once I have all those resistances down, I can then write down some equations. So generally I have 3 unknowns, J1, J2, and J3. I generally know the temperature. For example, I know the temperature of object 1, object 2, and object 3. So I know all my EBs, but I don't know all my Js. And so to find all my Js, I generally write down 3 equations for 3 unknowns. And that's basically taken at each node. So I have node 1, node 2, and node 3. At each of these nodes, I can write down an expression that looks something like this. So I basically said all the energy coming into the node has to equal 0. So I'm assuming all my energy is flowing in. So energy flowing in from EB1, flowing in from J2, flowing in from J3. But I know energy balance, essentially whatever comes in equals whatever's going out. I just don't know which way things are going. So I call everything going in. So that means some of these are going to end up being negative, and that just means they're going out. But anything going in has to equal 0. So EB from the orange line, EB1 minus J1 over my resistance of 1 minus epsilon 1 over epsilon 1 A1. J2 coming in this line has a resistance of the shape factor 1 over A1 F12. And then same thing for J3 coming in. I have this resistance of 1 over A1 F13. And so again, all that equals up to 0. So in this equation, I know my EB, I know my epsilons, know my A's, know my shape factors. The only thing I don't know is J1, J2, and J3. So basically I have one equation for 3 unknowns. Do that at node 2. Again, similar equation. You're going to have another equation. I know everything in that equation except for my J's. Do that for J3. Gives me now 3 equations and 3 unknowns. So 3 equations, 3 unknowns. I can solve for all my J's. Once I found my J's, I can then find my energy being emitted from each surface or going into each surface, basically from the orange line, this term right here essentially. That is the total energy being lost or gained by object 1. I can do that for any object. So in general, QI, total energy, EBI minus JI over 1 minus epsilon I over epsilon I AI. Now, a couple of special cases that we ran into, and these actually make my radiation network a lot easier to deal with. They generally get rid of one of my unknowns. So instead of having 3 equations and 3 unknowns, I end up with only having 2 equations and 2 unknowns, which is much better. So these special cases, first one, if it's perfectly insulated or re-radiates all the incident energy upon it. So if it's insulated, basically means nothing's being absorbed. If nothing's being absorbed, then there's 0 resistance between the EB and the J. So if there's 0 resistance, that means that J1 equals EB1. So again, if I know the temperature T1, sigma times T1 to the 4th is EB1, and that's equal to J1. So that is my first unknown. That leaves me with only J2 and J3 that I don't know. So again, this is assuming that this object number 1 is this special perfectly insulated surface. Similarly, if a surface is very large, area goes to infinity. That resistance, again, basically goes away, meaning 0 heat flow. 0 heat flow, again, means that J1 equals EB1. So in either case, I end up with my J equal to EB for that particular object. And my, as I said, network diagram is a lot simpler, only has 2 equations and 2 unknowns. Another special case we dealt with are radiation shields. So if we have some object number 1, another object number 2, some heat flux Q over A going in. If I want to reduce the amount of radiation being transferred between object 1 and object 2, easy thing to do is put a shield down in the middle of them. So this doesn't actually add or remove heat. All it does is give me an extra source of thermal resistance. So again, if I'm actually setting up the radiation network for this, I need to get off of surface 1. So I'll have a resistance that looks like 1 minus epsilon over epsilon A. I then need to see this object or get to that object. So that's 1 over A1F1S in this case, then need to be absorbed into this object, need to be radiated to the other side, then see object 2, then be absorbed into object 2. So as I was saying, if I have my original objects, object 1 and object 2, the resistance network would look something like this. I need to get off surface 1, need to make it to surface 2, get absorbed into surface 2. If I have now put a shield in there, I'll have to make it off of surface 1, make it to the surface, the shield surface, get absorbed into the shield, get re-radiated, emitted out the other side, then make it to surface 2, then get absorbed into surface 2. So basically, this one term in the middle, 1 over A1F12, was replaced by these 4 terms. And generally, these 4 terms are going to have a lot larger thermal resistance than that one term, so much harder to get from surface 1 to surface 2, meaning much less energy being transferred. The other special case we saw was a transmitting medium. So if I have between object 1 and object number 2, I have some gas or something else that is somewhat transparent, so not completely transparent. So everything we did before this, we assumed whatever's between object 1 and object 2 either was a vacuum or didn't absorb any of the radiation between it. Now I'm saying that this medium can absorb some of the radiation. Some of it gets transmitted, some of it doesn't. The amount that gets transmitted would look like 1 minus epsilon, because epsilon, same as absorbing, and whatever does not get absorbed gets transmitted. So this is basically the transmission of the medium. In this case, G stands for gas. I'm assuming it's meaning the gas for this radiation network. The gas is very large, so generally you have some, instead of having a J for the gas, you have the EB for the gas, because I'm assuming the area essentially is very large. And then this is my radiation network, again, very similar. I have 1 minus epsilons over epsilon A's, getting off the 2 surfaces, and then 1 over shape factors, A2, F2G, for those guys. Only difference now, again, is that I have only some of it actually being absorbed and emitted from the gas, some of it being transmitted straight through. So if I went straight through, if there's nothing being absorbed, this epsilon is just 0. Sorry, epsilon is 1. No, I never said it right the first time. Epsilon is 0, nothing's being absorbed. And so I go straight from 1 to 2. I don't even bother going this way because there's basically an infinite amount of resistance. So all I have is this one line. Again, very similar to what we had before on the last slide. When stuff actually is absorbed, that's when I get this transmission factor and this absorption factor in my radiation network. The last special case we dealt with was reflection. So again, this is the reflection case that I said will not be on the test. So as you can see, reflection makes things much more complicated in terms of things can get reflected off things. There can be either specular or diffuse reflection, which actually changes things as well. And so I need to worry about a whole bunch of stuff that we're not going to worry about for the test purposes. So that, again, something we covered, but won't be covered for the exam purposes. So having said that reflection will not be on the test, what I meant was that previous slide we had with this really complicated reflection network. I could have a question like this. So this technically involves reflection in the sense that I have this material, has a transmissivity of 0.1, and has reflectivities 0.2 for the specular part, 0.3 for the diffuse part, and I want to find what the emissivity is. So this nice simple equation, again, I know that everything, entire fraction of energy being emitted is either being absorbed, reflected, or transmitted, and I know the absorptivity is the same as emissivity, and so I know the emissivity, absorptivity, I know the reflection, which is both the diffuse and specular added together. I know the transmissivity, sorry, I'm trying to find the absorptivity or emissivity. So emissivity is just 1 minus transmissivity and reflectivity. So 1 minus the 0.1, the 0.2 from the specular part of reflection, 0.3 from the diffuse part, leaves me with 0.4 for the emissivity of this object. So nice, simple, one calculation. Example of kind of a question you see in the multiple choice part. Again, this is kind of an easier one, but everything you see in multiple choice should be just kind of the one simple equation calculation. Examples of the kind of medium length question involving kind of 2-3 calculations. First example, have a certain emerald, has a transmissivity of 0.83 for every wavelength between 2.2 and 9.7 micrometers. And I'm assuming it's going to be 0 for all other wavelengths. I want to know the heat flux per unit area that comes through this emerald at 500 degrees Celsius. So a couple things we need, lambda 1 times T. So I want to find the fraction of energy emitted basically between 2.2 micrometers and 9.7 micrometers. So 2.2 micrometers, 500 Celsius is 773 kelvins. So that gives me 1701 micrometer kelvins for my lower bound. Upper bound, 9.7 times 773 gives me about 7,500 for my upper bound. And then from table 12-2, at 1700, I find that EB from 0 to lambda 1, which again is what they call F0 to lambda, that fraction is 0.02853. For the upper bound, 7,500, I get 0.83436. And so my total heat coming through, sigma epsilon T to the fourth. I called this epsilon, but if you remember the wording of the question, it said how much do you expect to see coming through? And so coming through is kind of the transmissivity. And so even though I called it epsilon, really I should be calling it tau because that's what's coming through the emerald. And so I have sigma 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. This transmissivity of 0.83, temperature 773 Kelvin to the fourth power. And then these fractions, 0.834 minus 0.285, 0.85, gives me a grand total of 13,540 watts per square meter coming through that emerald. So again, there's one example of kind of calculation you need to do, a few steps, but not too long. Same thing for example 3. I have two concentric discs, both have a diameter of 60 centimeters, separated by 50 centimeters. My second disc has a hole in it, 40 centimeters in diameter. I want to know the view factor, so what's F12 between these two objects? So again, this is an example of I have a table for two concentric discs, but I don't have anything with a hole in it. So what I have to do to find this guy, F12, is essentially take disc 1 and a entire hole, as in complete disc number 2, find the view factor between those, and then find a view factor between disc 1 and the hole, just the hole. So essentially I'm going to find a view factor between two 60 centimeter discs, and then subtract away a view factor between a 60 centimeter disc and a 40 centimeter disc, and that'll give me the view factor that I want. So for my solid, that's what I'm calling the, assuming both discs are completely solid, both 60 centimeter discs. I need some L over R1. So L being the separation distance, 50 centimeters, R1 being the radius of 30 centimeters, gives me 1.67. R2, because I'm assuming my second disc is whole, again is 30 centimeters. Separation of 50 centimeters gives me 0.6. I can then find from the graph, page 600 something, 603 to 607, there's a graph. I find that F12 is roughly 0.22 for the entire complete disc view factor. The other way I can do this is with an equation. So the equation given, again, close to those pages, I have the same sort of setup where I need this radius over the separation between them. And then find this value of S, which depends on those numbers for capital R1 and capital R2. And F12 in that case is given by this equation, gives me 0.11. So again, this is the view factor between disc 1, the 60 centimeter disc, and just this 40 centimeter hole down here. And so my total view factor will be this first one, the 2 complete discs, minus the hole, and that's going to give me the one I care about. So 0.22 minus 0.11 gives me 0.11 for that view factor, for that more complicated arrangement. So again, a couple calculations involved. That's my short or medium length open question, another example of that. Then last up, example number 4, this is kind of similar to what you'd see for the longer version question. So multiple calculations are going to be involved here. I have 2 parallel square plates, 1 meter on each side, separated by a distance of 50 centimeters, completely surrounded by a large, perfectly black room. Shape factor between the plates is F12 is 0.4. Both plates have an emissivity of 0.8. One plate is at 300 degrees Celsious, others at 20 degrees Celsius. I want to find the net heat transfer between the 2 plates. So in this case, I have technically 3 objects. I have plate number 1, I have plate number 2, and I also have the large black room. So because the large black room is large, I can still call that infinite area. Infinite area, as we saw, the J is just equal to the EB. And so I know that the area of the 2 plates, area 1 and area 2, is 1 square meter. Plate number 1 is what I'm going to call the hotter one, the one at 300 degrees Kelvin. So EB1, sigma times T1 to the 4th, 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4th power, times 573 Kelvin to the 4th power, gives me 6,100 watts per square meter from the hot plate. Colder plate at 20 degrees Celsius is 293 Kelvin, so same deal, gives me 418 watts per square meter for the second plate, EB2. And then I know the view factor from 1 to 2 is 0.4. That means that the view factor from 1 to 3, so my object number 1, 40% of its energy hits object number 2. These things are perfectly surrounded by the room, and so whatever does not hit object 2 is going to hit the room, object 3. And so 40% of it hits object 2. That means 60% of it hits object 3. And same thing for object 2. Since they have the same area, have the same view factor of 0.4. So F12 is the same as F21. Now I have all my view factors between all my objects. What I want to do now is calculate all these resistances. So for my radiation network, again, from object 1 and object 2, I have this emissivity-based resistance. And then between all 3 objects, I have these view factor-based resistances. So calculating all of those, all the view factor ones, A1, F12, area is just 1, F12 is 0.4, so that's 0.25 for that guy. Between objects 1 and 2, that's this resistance down here. A1, F13, again, A1 is 1, F13 is not 0.4, it's 0.6. So 1 over 0.6 gives me 1.67, as we can see for A2, F23. So A1, F13 between object 1 and the room, this is 1.67. A2 and F23, so between object 2 and the room, also 1.67. Like it should be. So again, it's the right number. I just didn't type it right up there. And then these resistances from the objects themselves. So they both have an emissivity of 0.8. So 1 minus 0.8 over 0.8 times 1 for the area gives me 0.25. So both this resistance is 0.25 and that resistance there is also 0.25. The resistance to get from EB2 to J2 and similarly from EB1 to J1. Total resistance now. So I want to go from object 1 to object 2 or vice versa. So I have to go through this guy. So I have to go through the 0.25. Then I have a choice to either go through this line, which is the 2.5, or I can go through these 2 lines, which are each 1.67. Here's my parallel network for that. I can either go through the 2.5 or the two 1.67s. Then once I do that, I'm here, and to get to EB2, I have to go through another 0.25. So total radiative resistance, 1.93. Now once I have that, my total heat transfer is just the two EBs divided by my total resistance. So 6112 minus 418 divided by this resistance of 1.93 gives me 2,950 watts for the total heat transfer between the two objects. So you can see there a lot more calculations. So that is an example of my long open question. So that is it for radiation. As I said, next class will be the exam. Hopefully it's not that bad. As usual, any questions, feel free to email or post on discussion boards or whatever else you want to do.